Hello students, hope you are enjoying the lectures. We are going to move into lecture number 6, but before I start that, let me just tell you that you can always have questions regarding every topic I am teaching and post it to me by email. Anyway, we are going to create a website also which will be interactive so that you can understand how to use the interactive media. Nonetheless, let us start our lecture. Well, as you know, in the last lecture, that is lecture number 5, we have been learning about surfaces. We started lecture number 4, deliberated on lecture number 5, and in this lecture we are going to continue on it. As you know, surface and interfaces are very important for nanomaterials because surfaces or interfaces bear a significant part of energy of the system when the size is at the nanoscale. I discussed something about concept of surface energy, the bond making model, and then I discussed something about how surfaces, surface area affect the energy of the system, right? And finally, I talked about something about surface energy. So today in this lecture, we are going to talk about more about the effect of the surface energy. By the way, you have any questions, you can always write it down and post it to me. So what you have learned that every nanomaterial has surfaces, and surface area is pretty large, or surface area to volume ratio is pretty large, so the effect of surfaces cannot be ignored. Why it is, how it is manifested or how it is done? If you consider the surface atoms sitting here, okay, let us put a kind of a pen or something like that, and using a color. So if you look at any atom here, there are sufficient number of dangling bonds on this atom, and these dangling bonds are unsatisfied, and because of this aspect, because of unsatisfied bonds, these atoms are going to have more energy, okay? And when you have large number of such atoms on the sitting in the surfaces, then this energy is going to be significantly high, correct? So let us, this is very important for several materials, not only the carbon based one, but I like to show you this one because we know that carbon can form a single layer graphene, okay, where every atom of carbon is a surface atom, right? It doesn't have any connection with underlying material or on the top side, right? It's a single layer. So there are a lot of unsaturated bonds present on this surface of the graphene, and these unsaturated bonds carry a lot of energy. As you know, carbon atoms in the plane, they are connected with 4, right, each carbon atoms. But on the outside the plane there should be 2 bonds. These bonds are missing. Because these bonds are missing, so therefore there are unsaturated electrons present associated to each carbon atom, and they are adding up the energy of the system. So if you roll it up, you form a single wall nanotube, carbon nanotube. Again, the surfaces remains same. Instead of becoming a flat one, it becomes a curved surface. Or if you put several of these rolled layers, you can make a multi-wall nanotubes. Then you can have actually some of the bonds of the carbon atom on the top surface are satisfied. Well, this is something which is very important for every nanomaterial in this world. Okay, whether it's a carbon or some other species, doesn't matter. It is a aspect which is very common. Graphene is more predominant because many of these properties are basically because of these dangling bonds, like surface plasmons, thermal, optical, electrical, or mechanical properties of graphene. You understand, the graphene is much more stronger than a graphite, because graphite has van der Waals bonds between the layers, which are easy to break. But in the graphene, there is no van der Waals bonding. It's basically a covalent bonded carbon layer. So that's why elastic modulus of graphene is in the terapascal regime, not in megapascal or gigapascal. This is the reason, is this. So there are many such properties which we will discuss in some of the lectures later on, are because of the surface energy of graphene. Now, I also discussed about the origin of surface energy. Origin of surface energy is because of the breaking of bonds, right? So every atom is connected to the other atom via some bond. We have already talked about it about carbon. And so if I break a bond, and if the bond energy between the two atoms are U, then basically per atom you are spending energy of U by 2 or epsilon by 2, correct? So these bonds which are broken to create a surface, or these bonds which are dangling actually in case of surface already created, are responsible for surface energy, right? Or it can happen for interfacial also, interfacial energy also. So we have done some mathematical analysis using spherical particle, and we have shown that the surface energy depends on inverse of the size. It also depends on density, depends on the total surface energy, depends on the molecular mass, but most importantly scales with the size. That's the critical aspect, okay? So as you decrease the size, U surface increases. You see, U surface will increase as you decrease the size exceedingly at a very high rate, okay? So that's something which is also an important aspect. Not only size reduction leads to increase of surface energy, but it scales with the size. So therefore, we need to understand how does it scale with different kinds of shapes. It is only true for spherical one, but what will happen if you have a cuboid, or you have a cone, or you have a cylinder? That's something which we'll discuss today. Well, not only that, if you have a surface, atom sitting on the surface on a solid, okay, these atoms are feeling some kind of extra force because of the dangling bond, and this extra force is acting perpendicular to this surface, and this leads to what is known as a traction force, or in a larger scale surface stress. And surface stress basically will depend upon the stretching. Okay, how much these bonds are stretched is obviously because there is no bond on this side, the surface atoms will be stretched just like a rubber or a skin of a rubber, right? Exactly, it will be stretched. If you pull a rubber band, you are stretching the rubber band, so atoms sitting on the surface are also getting stretched. Exactly the same thing happens here. The moment you create a surface in nanomaterial, or any material actually for the sake of understanding, this surface atoms are feeling a force acting perpendicular to the surface, and this will lead to stretching of the surface atoms, and this stretching is manifested in terms of surface stress. And surface stress will be a function of stretching, amount of stretching, right? Then we have shown how to deal with it in the last lecture. I am not going back into that. Surface energy also depends on the orientation of the plane. I discussed this using a cubic FCC structure, and this is the formula which is used to calculate how surface energy will change as a function of orientation of the plane, okay, in a 2D. Correct? I think it's for you, two-dimensional situation is enough. You don't need to go into two-dimensional. 3D, it will have more complications, okay? But if you're interested, you can look into these textbooks which I have given. There 3D things are also discussed. Well, by the way, so these are the aspects you should know. Now, as if you can see that in this diagram, which is taken from Bolla's book of nanomaterials, it is shown how surface energy is going to change as a function of theta, positive and negative side. Okay, obviously sign it will not matter because sign is basically sine mod theta, but cos is going to be changing as a function of theta. This is, it gets two curves. Okay, you can see that, and this curves actually are origin of the variation of the surface energy as a function of orientations. So there are maximum minimum value of the surface energy because of orientation change. Okay, you can find out if your laboratory frame of reference is 0 degree, then at a different angle 30, 60, minus 90 or plus 90, how surface energy is going to be varying with respect to this angle. Well, now let us discuss of today's lecture. Surface energy also will depend upon shape. I already discussed about it, okay, for spherical shapes, right? So you can really understand why it will depend on shape is very easy to understand. Okay, so if I have a sphere and this is the diameter of the sphere, okay. So as you understand, the spherical particle surface area is 4 pi r square, right? Is it not? And that's equal to pi into, okay, let us erase it up, pi 2 r square, that's equal to pi d square. This we have done. And volume is 4/3 pi r cube, 4/3 pi r cube. I should be very careful because this pain always goes. That means it's about 4/3 pi r is d by 2 cube. So 4/3 pi into d cube divided by 8. So this is equal to pi d cube by 6. So V A by V rather is pi d square divided by pi d cube, 6 goes up, so it becomes 6 pi d. So if the say A by V is what? Area by volume ratio is function of 6 pi d. Surface energy also is scale as a function of 1 by d. Okay, 6 can be dumb distance as a constant factor. Okay, so this is true for if you have a spherical shape to triangular shape, cubic, hexagonal, or prismatic, or even rod like a cylinder, or even a helical. Correct? So by the way, you can create these shapes from a single entity by different treatments. You can create nanospheres, you can create nanoshell, you can create cube, even stars, nanorods, nanoclusters, or even branch structures, right? So all the geometrical things which you have learned in your +2 and even subsequent studies to calculate area and volume will come into picture, and we will have one lecture for this to how to calculate these aspects when we'll discuss more about it. Okay, that's an online lecture which I'll discuss more on that aspects. So let us see how it is going to be changing. Okay, I'll not do all of them. So when you refer to a singular surface area, we refer to this particle area of a single particle, right? Area is a function of square of the dimensions. All of you know that. Okay, it's as a unit of meter square or centimeter square, so inches square. So it will have a dimensions of any dimension, whether length or is a side of a cube or diameter square, right? Volume will have always a function of cube. So surface to volume ratio will be 1 by d, it is expected, but the constant terms will change. So dimension, as the dimension approaches or these particles become smaller and smaller, surface to volume ratio will be much higher. So now you can clearly see I have already done for spheres, it's 6 by d, right? What about cube? You can do yourself. That's very easy. If you cannot do, I can do. Yes, for you, that's something which is easy to understand. So I have done it probably, or let me do it again. There's nothing wrong. So if you know that Q has 6 surfaces and Q has each of these sides as a length of A. So surface area is 6 into A square. Why A square? A into A, right? So this is surface area of total surface area of the cube. Okay. Now what is the volume? Is obviously a cube. That I do not discuss even. So what is the area by volume ratio? It's 6 A square by A cube. That's everybody can do 6 by A, right? So now we can get it for where is like this, where has a diameter d, a length L. So you can do that, right? Or a cylinder, okay, or a disc, or you can do it for cone or pyramid, okay. So this is something which I think you should do. It's a home assignment for you. That's what I mentioned, right? If you do it for a wire, cylinder, disc, pyramid, cone, all kinds of shapes. Don't worry. If I'm not able to do, I'll do it for you. But you must try. You should try how to do it. This is very easy. See, idea is for you to do is that to understand how the surface to volume ratio is going to be critical for nanomaterials. If you create different shapes. So it gives you size is one aspect. Size of nanomaterial is one aspect, right? That's what we have been talking about it, size, right? But shape, which we have not discussed, is very critical. That's why different shapes has different kinds of manifestations in terms of properties. Well, if you can clearly see, if I plot surface area to volume ratio in nanometer units as a function of critical diameter or critical dimensions in nanometers for three shapes, sphere, cylinder, and cube. Let's see how it happens. For a sphere, I have already done is 3 by r or 6 by d, right? For a cylinder, it's very easy. Again, it is done here. Pi r square h by twice power h, and it's become 2 by r. For a cube, 6 by L or 6 by D, 6 by A actually, we have done. That's okay. L is the length, suppose, of the things. Okay, it doesn't matter. You can write down 6 by A also. Am I clear? So this is equal to 4 by T. Oops. This should be 4 by D, not small d, capital D. Oops, it's always like that. Right, 6 by D, 4 by D, 6 by A. So as you can clearly see, the change at which it changes, basically sphere and the cylinders, they are, well, all of their behavior is similar, but only difference is that the way they are changing. Okay? So as you clearly see, for the critical dimension of less than 10 nanometers, or rather 20 nanometers, the effect is very significant for all these shapes. But when it becomes very small, of the order of 2 nanometers to 3 nanometers, all of them will be having similar effects, not much difference. Okay? All the ratio will be almost between 2.5 to 3. But between 0.2 to 2.5, that's why most of the things happen. This is 0.2 actually. So you can see this something about 15 nanometers show the effects are very, very, very rapid. So that's why it's very small scale. The shape will dictate how the surface energy is going to be changing. This is something you should always remember. Okay, you should not forget that. Okay, so now I would like you to also plot, make the similar plots for other shapes like cone or maybe pyramid or disc. You can do it, right? This is an also home assignment for you. Just try. You can use computer to plot. Okay, you don't need to plot yourself, but just see how these plots will behave as a function of different shapes. If you can do it, all the different geometries in one plot and send me, it will be great. I'll be appreciating your efforts for that. Okay, so that's something which is very important. Now, I'm going to come to another important aspect. Okay, so we have spent about 20 minutes. So, as you know, all of you know about curvatures, right? Because we have been studying about curvatures from your class 2 or even 11th standard, right? Or 10th standard. Curvature has a very important effect because most of the geometries we see are curved. They are not flat. Okay, like you consider sphere, you consider a cylinder, you consider the pyramid, you consider a cone. They are all curved. They are not flat. So therefore, curvature is inbuilt in these shapes, and we should understand what is the effect of surface curvature on the surface energy. This is something which we will discuss in a detailed manner. Now let me just tell you that, as you know, surface energy is basically dictated by the bonds which are broken or dangling bonds, like the ones which are sitting here. You can see these atoms have dangling bonds like this. So therefore, they are having excess energy. So, we need to compute that excess energy. We will see how to be done. So, first let us talk about how surface curvatures are defined. Surface curvature is defined by this way. Suppose this is a curve. Okay, you can see outside one, this one I am talking about it, correct? I want to know the curvature at point C on this curve. So, what I do? I draw a circle which will be touching the point C. As you see, if I draw a circle, the radius of the circle will be r, right? So, therefore, local curvature at point C or radius of curvature is basically given by kappa, it is basically 1 by r, right, correct. So, therefore, this is what is very significant, right, radius of curvature. I think this is the local curvature. Radius of curvature is local curvature. Okay. So, radius of curvature is what? Radius of curvature is r. Okay, this is the local curvature. This is the problem with these panes. It's difficult to write. In a blackboard, you can easily write it up and so. And radius of curvature is r, right. Let me write down. Correct. So, as you know, there are two types of curvature, convex and concave. Traditionally or mathematically, we considered this K to be positive for convex. Okay, this is positive. And for concave, it is negative. This is what is traditionally accepted, because this has to be differentiated. Concave versus convex must be differentiated. To differentiate, we consider convex one as a positive curvature, concave one as a negative curvature. Am I right? So, that is what that is how we can differentiate. Now, remember these aspects. So, now question is, as we have began our discussion, what is the effect of the surface curvature on the surface energy, or in fact, how it is going to play a role? Well, change in surface energy, as you should know, change in surface curvature will lead to change in free energy, and this is written like this. Okay, this is very easy. This is equal to change in pressure multiplied by volume. What is the meaning of that? Let us consider this one is basically a soap bubble. Now, delta P is nothing but pressure difference from inside and outside, that is P2 minus P1. If P2 is the pressure inside, P1 is outside, then delta P is P2 minus P1. And V is the volume, right, that is understandable. So, this can be written as like this, twice gamma, this is gamma, this is not R. Now, I have to change the symbol of R, gamma by R into V, right. This derivation of delta P equal to twice gamma by R is you have done in your class 2 standard even. Okay. If still not able to understand, we can do it when we discuss about this lecture. But for the sake of time constant, let us consider this is the delta P. So, as you know, delta G is inversely proportional to R. So, as the psi decreases, R decreases, delta G increases. Even if gamma is not changing much, gamma will also depend on many aspects, but assume gamma is not changing on those aspects. So, delta G is a strong function of R, inversely proportional to R, right. So, inside, so now this inside pressure P will also depends on the kind of curvatures, whether convex or concave. In case of convex, it will be positive. In case of convex, it will be negative. That we have already discussed, right? So, delta G, sign of delta G will be changing depending on the type of surface. In one case, it will increase the energy of system, other case, it will decrease the energy of system, right? That is clear. And this is coming from mathematical treatment of convex and concave curvatures. We have to differentiate between them, right? So, therefore, this negative and positive signs are placed to that they are not same. You can also have a curve like this, right? You can see this is convex, this is concave. So, how this will affect delta G, you can understand. So, this part of the curve, convex one, has a positive delta G. This part of the curve will have a negative delta G. So, this will lead to even mass transport, energy transport, all kinds of things. So, now we are going to discuss a very specific thing, the effect of this delta G on equilibrium frequency concentrations in nanomaterials because of this curvature. Okay, I am going to derive it. Okay, so therefore, please listen to me and also try to follow my step. So, total energy, total free energy of any system, suppose we consider total free energy of any system, we will have two parts, right? One is your bulk and your surface, correct? Many people write this delta G surface as delta G excess. Excess means excess, EXCESS, okay, excess. So, we always write X as EX, right? Fine. And this one, this extra term is basically because of curvature effect. So, that we can write down gamma, this is capital, okay, sigma, right. This one is known as, this one is known as atomic volume, volume of one atom. Correct. So, I can write down delta G total is equal to delta G bulk plus this term, right. So, this is our equation 1, this is our equation 2, right. So, how many of you know how the vacancy concentration depends on delta G? You should know that. Okay, it is given in literature. So, you know the volume fraction of vacancy, which is nothing but xp total. X is always used as a fraction, right. Okay, this is not volume fraction, this is basically like a solid concentration we define mole fraction. This is equal to exponential minus delta G total divided by KVT. Now, I would like to discuss about this aspect. Why we use KVT? When delta G total is in, and it is given in EV, electron volt, you can use Boltzmann constant. It is given in joules, you can use R. R is the gas constant, right. So, both of these are correct. So, that is my equation number 3. So, I can expand this minus delta G bulk by KBT multiplied by exponential minus right. That is what it is, correct. Now, as you know, I can always write down xp bulk, the concentration of vacancy in the bulk, as exponential minus delta G bulk by KBT. So, this gives me, this one will give me finally xp total is equal to xp bulk multiplied by exponential minus that is equation 4. So, that means the xp total is depending on xp bulk and the exponential term. So, now next go to the next page. We will again write the same equation, you may forget. So, xp total is equal to xp bulk multiplied by exponential minus so, when you know when exponential minus, okay, let us do this maths on the right side, is x is very small, okay, then as you understand r is small, kb is small, but T is large, but this gamma is also very small, atomic volume, this sigma, correct. We can write down exponential minus x is almost equal to 1 minus x. You know, exponential can be expanded 1 minus x plus x square by factorial 2 minus x cube by factorial 3. I am just stopping at x, because if x is very small, other terms will be very small. Okay. So, I can write down this xp bulk 1 minus that is my xp total. Okay. Now, let us bring in the concave and concave surface effects. So, for the convex and for the concave. For the convex, this will be because r is or 1 by r is positive, this will remain same sigma gamma r KBT. For the concave, look at what will happen. This will positive because r is negative, so it will be positive. So, we can write down this as equation 5, this is equation 6, this is equation 7. So, for concave and convex, the huge difference. One case you are adding up this term, other case you are subtracting this term, right. So, therefore, one case the vacancy concentration will increase much more than what is the bulk vacancy. Other case it will decrease substantially, right. So, what we can write down from this? We can write down from this very simple thing, that xp total for concave must be greater than xp total, okay, when there is a flat surface or whatever it is, okay, flat surface. Convex. It is very interesting, right? If you have a surface like this, So, vacancy concentration will be large here, vacancy large. Here vacancy concentration small. So, vacancies will move from here to there, right. As the vacancy is moving here to there, mass will move from here to there. That's obvious, right. That is what something we should always remember, that is obvious, correct. So, this is going to happen. So, if you have a surface like this, which is most likely the case is convex, concave, convex, again vacancy will move, mass will move. So, if the mass is moving from higher to lower region, so finally whole thing will, this thing will become like this. They will join together. Well, you are not able to understand it more. Let me give you some example to make it clear. Before that, so that means the diffusivity is, diffusion is related to vacancies, right. So, diffusivity is, that is what we just talked about, it will depend on the size. So, this is convex, this is concave. So, as you see for the concave, vacancy concentrations will be more, diffusivity will be high, right. That is what it shows, and this depends on size. About beyond about 10 nanometers, so effect is not so significant, but below that effect is very significant. On the convex side, it is going down, okay. It is going down to very small values, diffusivity. This is normalized, means normalized respect to the flat surface, that is why it is normalized, okay. A flat surface has one diffusivity, that diffusivity is used to normalize diffusivity of the concave surface and diffusivity of the convex surface. And this is diffusivity of 900 in silver, gold, platinum nanoparticles are different size normalized with respect to bulk diffusivities. That is what I told you, bulk, okay. Oh, I am sorry, I told you flat, no, it is bulk. Bulk means there is surface effects are not there, it is a big size piece of gold, silver, platinum. So, you can clearly see how diffusivity at 900 is going to change. What is the effect of that? There is a significant effect on the sintering of nanoparticles. That is why if you prepare nanoparticles, even room temperature they will sinter. Well, let us look at it. See, that is what I told you, this is a curvature, just now I told. Convex, concave, convex. So, because of vacancy differences in between this point and this point, the convex and the convex, the vacancies will move, there is a concentration difference that will lead to migration of vacancies, and the opposite direction mass will move, right. So, as the mass moves, this particle will join one with the other. So, more and more mass will move from this top region to the bottom or to this part, and this will lead to increase of this particle size. That is what happened when something sinters, you can see that, okay. This exactly same geometry is happening there also at the atomic scale. So, I hope this part is clear. Now, some people have done experiment, this is taken from Dieter Bohlat's an experiment of sintering of 2 gold nanoparticles. Here you can see one nanoparticle here, one nanoparticle there, and then coming close, coming close, coming close, coming close, and they are joining here, and slowly, I think they are here joining here also they are joining, and then finally becomes single particle. This happens at room temperature. You do not need to do it at high temperature. That is the important aspect. That is mainly because of the surface curvature. So, as it become a curved particle, surface curvatures are going to change. So, you understand how important it is, the curvature, and most of the geometries we see having curved surfaces, and that will have different curvatures. This is something which you need to read and understand from the books also. I hope I made it clear how it is important by mathematical derivations which I did here, okay. So, these derivations are basically from thermodynamics we are using. Well, this is again shown in a detailed manner here. This is taken from Dieter Bohlat. you can see the negative curvatures, right. Negative curvature means concave, and convex will lead to positive curvature. So, mass will transport, you see here material transports will happen from negative curvature to positive curvature, and these two guys will join together. This is something which is easy to understand. This picture is very, very favorite picture of mine. You see, this is alumina particles, two alumina particles. Okay. Here even curvature will change the vapor pressure, okay, which I don't know, I may discuss next class. Till I am thinking about it. This is not part of a syllabus, but still it is easy to understand. Curvature can change even by Clausius-Caplan equation will bring about it. Curvature can change even your vapor pressure, and this will lead to change of mass transport. Something will evaporate from the convex region to the concave region and join, and neck will increase. This is also possible. Well, the last thing in today's lecture we are going to discuss in 5-7 minutes is how the lattice parameter is going to be changing, right. Right, that is something which you need to do. So, as you know, lattice parameters, if you do not know, let me just discuss about it. You know the unit cells, okay. In a cubic crystal structure, there is simple cubic, this is simple cubic lattice, this is stress centered cubic lattice, this is body centered cubic lattice, and you have also hexagonal crystal structures. These are mostly observed, that is what I have shown. So, in a simple cubic structure, lattice parameter is given by A. FCC also, this is the lattice parameter. Okay, BCC also, this is the lattice parameter. HCP, you have two lattice parameters, one is the C, other one is A, correct. But this is how the lattice parameter is defined. Now, because of the size, lattice parameter can also get changed. How? Okay, let us do simple mathematical calculation. Well, all of you should know that Gauss and Laplace, you know, they gave a formula about the pressure difference of a soap bubble, okay, and this is something which many of you read about it. Just now I did it. It's 2 gamma by small r, so that's become 4 gamma by d, and this is basically many people call, this is basically Gibbs-Thomson effect, Gauss, Laplace. Right. So, P is delta P is the pressure difference between interior of a liquid droplet and outside. Exactly same thing happened in solid soap bubbles. Now, we can always define another important parameter called K. K is known as compressibility. What is it? Well, compressibility is what? Compressibility means if I have a gas, 1 liter of gas, and if I apply pressure, how much compression I can do. This can happen for solid also, but it will be difficult, I understand. It can happen to liquid also, correct, but gas can compress easily. More you can compress, liquid can be compressed little less, solid can be compressed even much less. So, that means compressibility is a parameter which is very unique. This is used, and this is defined like this. V0 is initial volume, and this is done as constant temperature, that's why delta V by delta P. So, now let us consider a simple cube, okay, which has a volume of A cube, right. So, therefore, I can write down, okay, let me just not do it here, we will do this one. So, now I can write down K, so K 1 by V0 like this, right. While delta V is infinitesimal change, delta p is infinitesimal change. They are no longer differentials, but they are infinitesimal changes, correct. So, that is what I write almost equivalent to, k is almost equivalent to. So, now I know V, okay, V0. So, delta V is 3a square into dA or delta A, right, not dA, you should write delta A. Mathematically, it should be right, very clear. So, and you know delta P. So, now let us put together K 1 by V0 into 3 a square delta A, that is my delta V, and what is delta P? 4 gamma by d, where this is the diameter, like gamma is the surface energy. So, now I can even put the value of V0, right. So, that is equal to A cube and d go above, correct. So, I will simply simplify, which you can do. Let us do that. So, this a q a square get cancelled, correct. So, delta A by A, delta A by A, this becomes 4 gamma k divided by 3d. Am I right? That is what it is. Or you can write down this way also, gamma by d is gamma by d is equal to 3 by 4 k delta A by A. So, this is your lattice parameter change, correct. So, that means if gamma is finite, k is finite. So, lattice parameter change will depends upon 1 by d. A 4 and 3 are constant, gamma is also can be considered constant, and compressibility is obviously constant for a particular material. A is lattice parameter in the bulk. So, for the lattice parameter change, it is 1 by d. So, you can clearly see as the particle size decreases, lattice parameter will also change, and it is been observed that as the particle size decreases, lattice parameter decreases compared to the bulk, and this can be explained using this formula I have given it. Okay. That will depends obviously on delta A by A value, because as you see delta A by A, this is depends on the value of compressibility gamma, they are very small scale, and d the ratio. Okay, if compressibility is negative, delta A will be negative. If compressibility is positive, delta A will be positive. For most of the solids, that is what is happened. This is for aluminum as a function of particle size. So, what do you understand from this lecture today? First, we discussed about effect of shape on the surface energy, how it is going to be changed, and depending on different shapes, you have different kinds of formulae. Then we discussed about the curvature. Depending on curvature, surface energy is going to be changed, and that will lead to change the vacancy concentration, and this in turn will affect the diffusivity, and diffusivity will then affect the sintering of nanoparticles. And this is so strong, the effect is so strong, even at room temperature nanoparticle can sinter, like gold, platinum, silver have been found to be sintering. And then finally, I discussed about lattice parameter effect, or the effect of psi in the lattice parameter. We will continue discussing on this in the next lecture. Okay, thank you.